This is an important feature, especially if you want to monitor over the time, okay? So the radar data, as you see here, two images, one acquired by Maris on board Envisat is a multispectral imaging system, and the ASAR system on Envisat, they were both present in the same time on the same area here, and you see the very the nice feature of the radar to penetrate the clouds and provide information almost everywhere. So this is a first elementary aspect that makes it very suitable to observe dynamic processes over the time. So each time we pass, we acquire information, and typically we have not to throw away 50% of the data because of the cloud coverage. So this is the first aspect. And second aspect was the fact that we are able to, by exploiting a principle of synthesis of a large aperture, okay, we are able to generate images which have a very high resolution. So the fact that we can synthesize antennas of the order of 4 kilometers up to even more gives us the possibility to achieve 3-meter resolution or meter resolution over the ground. And so to generate images like this one, okay? So this is an example of Cosmos Sky-made images. Spotlight was processed by us. And you see here, it looks like an optical image without colors, but it looks like, with the details, comparable to an optical image, to a very high resolution optical image. And so please keep in mind that we are working at the frequencies which are 10,000 or 100,000 lower than the optical frequencies. So we are decreasing the frequencies of a factor 10 to 4, 10 to 5, okay? Nevertheless, and Professor Pascazio told, we are increasing the wavelength, 10 to 4, 10 to times. Despite this increase, by exploiting the principle of a synthesis of an aperture, we can generate images which looks with the same details as the optical data. So this is a very nice point, and what we do? Essentially, we exploit the information that the radar pulse is a coherent radiation. Okay, so we use a coherent radiation, and here is the difference you see between incoherent radiation used by the optical system and transmitted by the sun, whereas in the case of radar pulse, we are able to control the oscillation of the pulse, okay? So we not only care about the envelope of the pulse, but we are able to control the oscillation of the radar. In our jargon, we say that we are able to control the phase. The control of the phase means we are able to discriminate if we are in the peak or in the valley of the oscillation, okay? So this is a very big difference, and this features allows us to gain and to retrieve back the resolution to be comparable with the optical system. So this phase information is important and is exploited for the synthesis of the aperture. Okay, here just a slide that shows which has been the development over the year of the SAR sensors from the satellites. Everything started more or less for regular observation with the ERS-1 and ERS-2 from the European Space Agency. Okay, and we go up to now that you see the more the time, so the more we come to the current days, then with the higher the number of satellite systems that are using sensors, synthetic aperture radar sensors that observe the Earth. And you see also emphasized the Cosmos Sky-made constellation, which is operated by the Italian Space Agency, starting from 2007, and the Sentinel, which is the continuation by ESA, that will be the subject also of the demonstration in the second part of the afternoon session. But what is important is that if you look on the right, do you see also sentences which have been taken by the internet, and you see how is growing the interest of private companies in developing satellites, compact SAR systems operating from satellites. So you see on the left, essentially what has been the growth, mainly managed by the European Space Agency, but you see here that the market is sensed and is considered to be interesting also from companies that now have started to build up small satellites and launch into the orbits. This is a very interesting point of the discussion. Star images are two-dimensional. We talked this morning. With the SR system, we are able to provide images which are two-dimensional. We discriminate the range, so the distance from the orbit, and the position of the target along the orbits, what is called the azimuth direction, okay? But nevertheless, the reality is 3D, and so how to discriminate the third dimension, that for a radar means the angle under which a target has been seen. This is possible essentially exploiting a principle which is very similar to the human visual system. What we do, if we have two eyes, okay, and then we have two image planes, if we have a target which is close to our eyes, then we see that the position in the image plane of the projection of the target are quite different. You will see in the slide, one is close to the border and one is close to the center. Whereas if the object gets far, okay, then the two positions in the image planes are more or less in the same position. So what we do with our eyes is tentatively we compare how much a projection of an object changes from one image plane to another one. So if the object is close, then we see a large variation. You can try also by closing an eyes and moving. And if the object is far, then the two positions are closer. So what is important, what matters is how much it changes the position of the target in the image plane from one image to another one. Okay, and the radar more or less single star image in which we have the ambiguity, because if we measure just a distance, okay, in the orthogonal plane to the orbits, then we don't know which of the target has been illuminated. We exploit the fact that we look at the scene from a slightly different position, okay? And so we measure two ranges. And what is important is that if we measure two ranges, then if we cross the two circles at the given ranges, then there is only one point that shares the given distance from the first satellites and from in the second image. But what is important also in the radar is how much the range changes from one image to another one. It's exactly like in the human eyes, how much the projection changes from one point over another one. This is the third information about the depth. And here in the radar is how much the ranges changes from one image to another one. This is the quantity that is directly related to the height of the target. So we need to measure the delta R, the changes of the range, but it is not sufficient to measure the change of the range by working only with the envelope of the pulse as discussed before. We need again to bring back to the phase, okay? And only the phase information provides us the accuracies in the measurements of the change of the range between two images. So here again, we have the envelope of the radar pulse, and we have two images. If a target changes the range, and if we are able to sense the phase, that means we are able to discriminate if we are in the peak or in the valley of the oscillation, then we measure the change. And we measure the change with an accuracy which is on the order of the wavelength, because the oscillations runs with wavelengths, okay? So we get measurements of the variation over the range, which are on the order of centimeter. And this is enough, okay, to provide the right information on topography to the accuracies which is required. So this image I usually show to explain how the phase, that means the measurements of the variation over the range, follows the topography. So this is what is called an interferogram. So each time we go from a peak to a valley, then we have a change of the color. So this is called interferogram, okay? And so the interferogram you see here, if you plot the interferogram, that is the phase change from one image to another one, and overlay with an amplitude image, you already get information about topography. So it's very nice example of how alone an interferogram follows the topography of the scene. So this is for what matter the measurements of the topography. But what happens if we acquire one image, and if we acquire a second image exactly in the same point? We do not change the angle of view, but what happens? On the ground, there is a target that is moving. And of course, the principle is the same. If we follow the phase gives a measurements of the range variation to an accuracy which is on the order of the wavelength. That's very nice, because with this system I can measure variation of the range, okay, which are on the order of the fractions of the wavelength. And this is the principle of what is called differential interferometry that gives us the fourth information. So not only 3D, but also the possibility to measure the movement over the time. So just to give an example, this is an example with which we measured the deformations of the L'Aquila earthquake in 2009. Okay, here there are also people from the IGV, so in the National Geophysics and Volcanology Institute from Italy. So they remember that time in which there was this earthquake, and here the equiphase lines, the interferogram measures the deformation. So each curve, when we move from one curve to another one, measure a phase change which is lambda over 2, so the wavelength over 2. The wavelength is 3.1 centimeter in this case, so the phase change measure 3.1 divided by 2, that is almost 1.55 centimeters. And so if you count the phase change, then you can measure the deformation. Modern approaches, how they work. Yes, please. The magnitude of the earthquake was around 6 or 7, something like this. 6, yes. Yes.
So can we detect anything which is less magnitude than 3?
This is becomes a problem.
Okay.
This starts to become a problem. Typically, it depends also on how much is the depth of the earthquake. If it is so the amount of deformation that gives on the surface depends also on the depth of the source. Okay.
So it depends on the displacement, not the magnitude. Like any kind of earthquake might make some displacements in the surface, right?
Yeah.
So it should be picked up by the interferometry, irrespective of what the size of
with these measurements, you measure the change of the deformation. You can use model for the inversion of this to provide the rupture on the fault plane. So typically what they do, they measure the geometry of the fault, okay, and then they fix the model, and then they invert a model with respect to the rupture that has occurred on the fault plane. It is called, so they are able to invert and determine how much was the change on the fault plane.
Okay, great, thanks.
Okay, well, welcome. The slip, it is called, slip. I didn't remember the name. It is called, the rupture is called slip. So with the current approaches, what we do, we have satellites, they are orbiting in the polar orbit, so they acquire, each time we pass, they acquire information about radar images. We can collect this stack of radar images and process all the images together in order not only to detect a change from one point to, so one image from another one, but to monitor the deformation over the time. And this is the task addressed by the modern multi-temporal, what we call multi-temporal differential interferometric technique. We generate different interferograms, process in a quite complex way, and we are able to monitor the deformation over the time. And this, again, I go back to, also because there is an Italian Space Agency, otherwise I would have used another sensor. Again, back to Cosmo, in which now we process, and at that time the sensor was only made by 3 sensors. They were able to acquire 1 image almost each 5 days for 6 months. And we collected all the information, and we were able to monitor the deformation over the time. And you see here a very nice example in this area here, in which we measure the time series of the displacements for the main shock and for the aftershock. And you see typically the decay of the deformation over the time for the aftershocks. So this is a quite typical behavior in which you have a decay of the displacements over the time. What was interesting here, you know, this data demonstrated that what we had in this case is that the main shock produced a rupture over the ground on the fault plane, but all the aftershock produced the upper part of the fault to rupture. So it was the aftershock, they were located in the upper part of the fault. So very interesting and exceptional data set that allowed to do this kind of monitoring. Of course, you cannot monitor only earthquakes, but we use quite regularly to monitor, for instance, landslides here, and you see on the left an example, but you see also the capability of monitoring infrastructure, and in this, of course, the spatial resolution is an important factor here. With the Cosmo, typically you get a spatial resolution which are on the order of 3 meters. You can go even beyond, whereas with the oldest sensor, we had resolutions which are on the order of 10 meters, and of course, the spatial resolution, let's say, plays a role in the measurements of the density of the point. Here there is another example of, it was also shown before by Professor Parcazio. This is the Mirage Hotel. The sensor is not Cosmo Skymet, unfortunately. But in this case, with the spotlight data, with 1 meter data, we reconstructed the 3D positioning of the Mirage Hotel in Las Vegas. We call it radar scanner from the space. It's like a laser scanner, but located on the space, and uses the radar radiation to reconstruct the building, I think. And this is for the demonstration. In the demonstration part, we will show examples provided by the monitoring with the live, in which we can play with the GIS and ask for the measurements of the deformation with the Cosmo Skymet and with the Sentinel. Sentinel is the new sensors of the ESA, which works at C-band, so a little bit higher wavelength with respect to Cosmo Skymet, so lower sensitivity. But what is important in the case of Sentinel is the regularity of acquisition. So Sentinel has a lower resolution, but it can, let's say, use this lower resolution to image larger areas, and so each 6 days it acquires information regularly, and this is an important aspect, the regular monitoring also from the processing point of view. Okay, thank you very much for the attention. I don't know, you have questions still? Yes?
So, what is the difference between the DSR and PSI? Which one more reliable?
PSI, it's just a matter of different processing algorithms. The class is always multi-temporal differential interferometry. So they always use the phase information also. The main information is the phase information over seconds of data, and there are different approaches. There is persistent scatter interferometry that was first developed, but also there are different other approaches like small baseline approaches, and we have different classes. It's just how we process and extract information from the data.
So you mean PSI came first and then DSR, or the opposite?
Now, typically what we do is we use, let's say, lower resolution approaches to retrieve what they are called the atmospheric. I told you they can penetrate the atmosphere, but actually they are lowered by the atmosphere, okay? And this lowering is measured as, an error in the timing, okay? So typically you have the effects of the atmosphere as additional fringes, which you have to estimate and remove if you want to measure the deformation, okay? And so typically you work with this, then you calibrate for the atmosphere, and then you can use PSI, or you can use tomographic approach to make a 3D synthesis. For instance, the Mirage Hotel, it was made by using a tomographic approach in which we make a synthesis of an antenna also in the third dimension, so that we can sear the beam, and we can solve also layover problems and all the other stuff that is over there. No, with different sensors it's quite difficult because you need to keep coherence, and coherence means spectral resonance. And if you combine spectral data which come from different bandwidths, they do not resonate one with respect to another one. Okay. You're welcome.
Okay. Thank you, Gianfranco, for this really... Thank you, Gianfranco, for this really interesting presentation. For the rest of the other questions can be posted at the end of the demo that will treat the same topic. So Gianfranco will show both experiment from the Cosmos ChemEd and Sentinel-1 data. Move to the second presentation of this session. The speaker is Professor Paolo Gamba from University of Pavia, and the title of the talk is Material Characterization Using Hyperspectral Prisma Data.
Okay, so thank you, Professor Pascazio, and thank you, everybody, for staying here. I have the advantage with respect to my colleague because, you know, talking about hyperspectral, there is no matter, you know, there is only one sensor right now, so that's it. So that's why I'm using material characterization using hyperspectral prisma data. So let's start with the concept of hyperspectral images. As I mentioned in the morning, when we talk about multispectral, we basically start from the spectral signature of a specific material, and we take a few measurements. When we move to hyperspectral, what we have is we have a very large number of spectral measurements, spectral band. So every single pixel, which is the one which is mentioned here, is basically, and also here as well, okay? It's basically a very long spectral vector. The disadvantage is since, as I mentioned this morning as well, when we have the same quantity of energy and we take a lot of slices, then basically what we have is that each of these slices is getting a smaller amount of energy. Therefore, the spatial resolution, so the area that you have on the ground for an hyperspectral sensor is larger. So you don't get the same amount of details because you have to slice this energy here. Okay, so when you get the multi versus hyperspectral spectral data, you see that this is the fact. For multispectral, you have only a few measurements. This is similar to the image that it was in the morning. This one is what you get when you have all the data. This is an airborne sensor. Okay, so the average is a legacy, let's say, sensor from NASA. And the spectral resolution is much more detailed in hyperspectral sensor. And of course, this gives us the possibility of a better spectral response. But it comes, it says, at the expense of a spatial resolution. So we have something like this, that when you have only a few points and you try to reconstruct everything, this is common on signal theory that everybody in electronic engineering does, or computer science. You have only a few points, you cannot reconstruct the whole wave, the basic structure. If you have many, then you get something which is better, okay? So what we need is basically to understand what it is possible to extract. So here we have an example of prisma data taken over the area here of Dubai. This is not just one image, there are 3 images, 1, 2, 3 images. They are not taken exactly at the same date, but luckily there is no big change in terms of things. And you see here, I have plotted, really my PhD student has plotted, the spectra of what we get with respect to the spectra that we have collected in some specific database. Here, the USGS spectrum database is one of the most important. And you see clearly that here you have, this is what you get. And this, for instance, the green one is a measurement of concrete. Okay, of course, it's not exactly the same. Why is not the same? Because hyperspectral is not like SAR. It has a very big dependence on the atmosphere. So you get some points that do correspond to areas where we cannot get that specific wavelength because it's an area where the oxygen or the water, which is in the atmosphere, is basically taking all the energy, so you don't get anything, okay? But here you see very clearly that we are able to reconstruct the concrete. Here it's even better, vegetation. And here is water. Okay, water is very well known to have a spectral response which is going down when you go to the infrared, okay? And this is just to give you an idea. And I must admit, this one is the original image. It was not corrected by the problems of the atmosphere. So you can get something which is even better than that. Now, talking about what we discussed this morning, using the fact that we have different bandwidth, we can extract different colors. And since we have many bandwidth, we may have many false color image. And even when you think about true colors, we think red, green, and blue. But you also could have many reds, many green, and many blue, because every single... So it's not like, you know, our colleague in the morning, they showed us NDVI. We show you that actually with hyperspectral, you can have multiple NDVI. Depends on which near infrared, which green, which red you are considering, and you get slightly different things. And this is interesting. Okay, different colors provide false color combination, and you get different colors. Okay, here is same example, same images, taking some iconic places that everybody knows about Dubai. So Burj Khalifa, the Expo, and some of the islands that you have, also one of the palms. And here you have both the true color and some false color image. Of course, it's one of the, let's say, numerous possibilities that we have to extract that. And the demo that I'm going to give you the possibility to access is basically you can see some of this false color and just look around and connect. And since some of you are locals and some of you maybe are interested about these different areas, you can just play and see what's there. Okay, just talking about NDVI in a moment. You know that this is the vegetation characteristics, which is given by the first part, which is mainly the visible part, which is related to the pigments. So this morning I was talking about chlorophyll. Then this one is basically related to the crown and the leaf structure. So depending on, you know, lot of leaves, small crown, you have different values here. And this part is mostly for the water content, because these are the bands where the water is basically absorbing the radiation from the sun. Okay, and here you have the NDVI that, as I mentioned, as this morning was shown, is a quantity that gives you ideas about the vegetation, because when everything is green, you get that the near infrared is very well backscattered, while the visible is mostly absorbed. When you go to something like this, then the visible is partially absorbed, but it's also reflected, and the near infrared is reflected at the same level. But it's very easy to understand that the value of the NDVI in the first case is 0.72 in this example, In the second case, goes down to 0.14. Okay, and here is the example of what you can get when you have an hyperspectral image. You can have not only NDVI, but something that is called NDVI 705. And of course, the reason why, okay, sorry, this is 750. But anyway, that's, it really depends on which one you are considering here, but it's okay, you can have both. So this is the standard definition of NDVI, where you use 800 nanometer for the near infrared and 680 for the red nanometer. And here is another one which has been studied by people looking for vegetation characteristics. It's not exactly my field because I mostly work on urban areas, but okay, I was looking and they say that this combination is much better. And you see that indeed, if you look at the two, you have different situations and that they do not exactly are the same. You can check by yourself on the demo that in some area you can see much better the vegetation here than in this situation. So if you use standard NDVI, but using hyperspectral, something like this. And another possibility which people have been considering is this other index, which is called EVI, so Enhanced Vegetation Index, which is a combination of different frequencies. So not only you see near infrared and red, but also going back to green. The last point that I'm going to talk to you and present you about hyperspectral is the fact that, okay, now the spatial resolution is a problem. The point is that if you have a spatial resolution which is not very good, when you take one single pixel, you don't get one single material. So it is clear that you have taken a forest and you take one single pixel, it's vegetation. In the middle of the sea, it's water. But if you take something in the middle of the city, is it concrete? Is it in another urban material? You don't know. So in that case, you have something which is a mixed pixel. So a pixel which is made by different materials. In this example, it's soil plus rocks or vegetation plus soil. The fact is that if you have a pure pixel, you have only one spectrum. If you have multiple, you have something which is a combination. So the point is, what can I do? In that case, we need to use an approach which is called spectral unmixing. So there is a mixing of the different, a mixture, let's say, of the different frequency. We need to go back. There are multiple problems here. The easy way is to assume that you have a linear mixture. That means that you have a pixel which is made by a percentage of a material, another percentage of material, a third percentage of material, and the final spectrum, the one of that pixel, is the combination of the spectrum of the three materials multiplied by the percentage. This is easy. I mean, it's an easy model. The problem of coming back, it's always a complex model because it's an inversion model, and every inversion model is ill-posed by definition. So we don't have a single solution. Then the problem is that the reality is much more complex because if you have this kind of a stupid example, but you know, it's a silly example, but it's a very interesting one. You have this kind of trees. You have a part which is coming from the material of the soil, the second part from another material, the third part by another material, but then you have always the combination. So you have a bilinear mixing. So you have mixture of two, but why two and not three? Why three and not four? You have something which is nonlinear, very complex. And this is typically what people working in hyperspectral are applying in case of extraterrestrial mission, where you have some information about the surface of the moon or whatever, of Mars. There you don't know what are the materials. So this is very complex. But this is also used in urban area, which is a very complex situation. So in any case, linear spectral unmixing, which is the easiest way, can be obtained by many different methodologies. This is a slide that I borrowed from one of my very good colleagues in Spain, Professor Plaza from Extremadura. He provided this one, which is a very basic idea of all the things. What we get is eventually that you don't have one single image, but you have what we call abundance maps. So maps that gives you, in every single pixel, which is the abundance of a specific material, starting from a linear model. Okay? And here we have an example applied to our Prisma data, where we took some elements of our area, and we have the abundance of concrete, the abundance of the first type of metal, and the abundance of a second type of metal. I don't know exactly what type of metal, sorry about that, but I need to do that. Yeah, it might be gold, and I guess it's not gold. But anyway, the problem is basically that, you know, we need some ground truth. So if we have someone who is... yeah, exactly. So we will send everybody to check what type of metal is there. But anyway, so this is exactly... And here you have, again, type of different materials. Okay, now, what I'm going to stop here and just giving you this slide where this QR code is also this one, which is a very teeny URL that gives you the link to the demo that we are going to use afterwards. Yes, there is a question. Yeah. Yeah, that's the point. That's the only hyperspectral sensor which is currently acquiring images. It's about, it's open access data. You need to register. You need to say why you want to have the data, but it's okay. And then you can download any data. So what I did is basically this one. I mean, no, there is not full coverage for UAE. Right now, there is a small amount of coverage for this area and the Abu Dhabi area. Maybe I'm wrong. Yes, you do. You can place any request, free of charge. That's why, you know, that's what this one of... Yeah, you need to be sure. You need to be a little bit patient because, of course, it's not happening tomorrow. Because the problem of not in Dubai, but I tell you in Pavia, that's my point, which is my area. It's because of the clouds. You know, if you ask 10% less of clouds, then of course you need to find when the satellite is passing, it's exactly 10% of cloud, and they get the. But for Dubai, you don't have problem with clouds. Not at all. Yeah. No. This one is 2021. Okay. Thank you very much.
Well, thank you, Paolo, for the interesting presentation, also for the interesting information about gold and about data that we can collect. So we will move after this session in order to search something. So we move to the third presentation. It is a remote presentation, so we can activate the connection with Professor Farid Melghani. Welcome, Farid, from University of Trento, and he will speak about remote sensing from drones. So I leave the floor, the virtual floor, to Farid.
Thank you very much, Vito, for the introduction. Good afternoon
Farid,
to everyone.
Because just a moment.
Yeah.
Try to speak again.
Can you hear me?
No.
No. And now, can you hear me? Now, can you hear me?
Not yet, Farid. Try to speak.
Yes, can you hear me?
Now we can hear you.
A bit better.
Speak, please speak.
Yes. Can you hear me? 1, 2, 3. 3, 2, 1.
Okay.
Okay.
You can start. Thanks.
Thanks to you, Vito. I'll try to share my presentation. Share screen. So can you see the presentation?
No, we cannot see your presentation. It's not shared at the moment.
What about now?
It's not shared. Non è condivisa la presentazione. Ma l'hai abilitato a condividere? Sì, ma non può condividere, non stai condividendo.
Farid, try
Yes.
to share the presentation.
Yeah, can you see it now?
Yes, okay. Thank you. You can proceed. Go ahead.
Thank you.
Full screen.
So thanks again, Vito, for the introduction, and good afternoon to everyone, and thank you for attending this event. So my brief talk, actually, it's about the evolution, so the recent evolution of UAV, so drone image analysis. So probably in the history, a first remote sensing image which was acquired is the one taken by a photographer whose name is James Black. So in 1860, from a hot air balloon over Boston. So the altitude was 2,000 feet, which means about 600 meters. A bit more recently, let's say, so 50 years later, probably we may consider them as the first living drones, actually, because here we are speaking about pigeon photography. So that is pigeons equipped with miniature cameras. So they were invented, or they were introduced in 1907. So here we have a picture taken in 1909. And they were mainly used for intelligence in World War I and II. More recently, we have obviously modern platforms like aircraft, like satellites, each with its own pros and cons in terms of cost, in terms of field of view, in terms of revisit time. And much more recently, we are speaking about 10, 15 years ago, at least for civilian purpose, came the advent of the drone, or the so-called UAV, so unmanned aerial vehicle era. So UAV have also pros and cons. Examples of pros are, for instance, flexibility, maneuverability, the customizability, examples of
Farid,
phones.
excuse me, Farid.
Yeah.
We are not able to follow your slides. Did you set the presentation mode? Because
Yes,
we are,
it is in
or
presentation
click
mode,
on the different slides. Okay, okay. Click when you change. Click on this. Okay, okay. Now we are on the third one.
Okay, so I can stay in this mode probably. See if there is a problem in the presentation mode.
No.
So is it okay like this? Can you see it? Vito, can you confirm that?
We cannot see you.
So let me stop the sharing again and redo the process. What about now? Is it okay?
No.
No. And now?